We're working through section 10.1, our learning target. We're trying to solve an equation of the form f of x equals c for a simple function that has an inverse, and then write the expression of the inverse. So we're going to be working with cubic and quadratic functions. So we've got a function that's defined with the following ordered pairs. So first thing we want to do is find the inverse of the function by reversing the coordinates. So that'll change to 4, -2, to -1, 0, 0, 2, 1, and 4, 2. So when we think about is the inverse a function, we're going to have to say no. It's not a function because two x values have different y values. Or we could use the vertical line test to check and see if something see if something is a function. So two x values have different y values. In particular here, if we look at 4, -2, and 4, 2, and then 2, -1, and 2, 1. So if necessary, we want to restrict the domain of f of x so that the inverse is a function. So looking back at the original coordinates, so the key here is we want to see where can we restrict the domain. So we look at our problem areas. That's when our x values for the inverse are 4, which means the y values of our original are 4. And then where the x values of the inverse are 2, so where the y values for the original ones are 2. So if we want to not make sure we have those doubles, we can just pick these 3 values, and then we won't have to worry about the doubles and the y values there. So in this case, we can restrict x to x being greater than or equal to 0. So we're picking only the positive values of x. So with the restricted value of f of x, what ordered pairs define the inverse? So again, taking the original coordinates, we're picking 0, 0, 1, 2, and 2, 4. So for the inverse, the new coordinates would be 0, 0, 2, 1, and 4, 2. So if we look again at the ordered pairs that define f of x, without reversing the order of the coordinates, how would you have known that the inverse would not be a function? Because if we look at the y values, we have same y values with different x values. This would be called the horizontal line test if you were looking at a graph. If it passes the horizontal line test, the inverse would be a function. So how will restricting the domain of f of x affect the range of the inverse? Well, because they're being switched, if the domain of the function gets restricted, the range of the inverse also gets restricted. That's again because they are the same. So working with a simple quadratic function, finding the inverse. So our function f of x equals x squared is many to 1, so its domain must be restricted in order to find its inverse. So we like to restrict the domain to the positive values, x greater than or equal to 0, so that way the inverse is just the square root. If the domain is restricted to the negative values of x, then the inverse would be the negative square root. So the inverse of a quadratic function is a square root function, which is a function whose rule involves the square root of x. The parent square root function is g of x equals square root of x. And so we're going to work through a couple of these. We want to restrict the domain. So first thing, we've got f of x equals 1/2 x squared. So first thing we have to do is restrict the domain. Then we find the inverse. So it's the same process as we've seen before in finding the inverse. First thing, you replace f of x with y. Now you're trying to get x by itself. So you'll have to multiply both sides by 2. And then you take the square roots. Again, the positive square root, because that's where we're restricting our domain. Now you switch x and y, and then replace y with f to the -1 of x. You can check this is true using composition, but we have decided not to do that. You can also check with a graph. So if you graph the inverse and its function in the original function in the restricted domain, and you should see that it is reflecting over the line y equals x. So they should always end up being a reflection over that line y equals x. So part B here, we want to find this inverse. So first thing, we restrict the domain. So we want to pick all x values such that x is greater than or equal to 0. Replace f of x with y. Now we'll have to add 7 to both sides. So we'll get y plus 7 is equal to x squared. Then we take the square root. We switch x and y. So we'll have the square root of x plus 7 is equal to y. And then just replace y with f to the negative 1 of x. And that is our inverse function. If you graph this, again, we're only going to be looking in the first quadrant because we've restricted our values. And it's going to look something like this. Let's see how I can do this. I didn't do a very good job. If you pull it up on your graphing calculator, you'll be able to see it. And it should be reflected across the line, y equals x. So we've got another example here. First thing we do is restrict the domain. So we want all x values such that x is greater than or equal to 0, positive values of x. First thing, replace f of x with y. Trying to get x by itself, so we'll need to divide by 3. And then take the square root. Now we just switch x and y and replace y with f to the negative 1 of x. And that's it. That's our function. You can graph this. Again, you can use your graphing calculator. I'm going to do a little sketch. It's not going to be very good, but it's going to look something like that. And it's going to be reflected across the line, y equals x. So we can actually use this with real-world models. So in many instances, quadratic functions are used to model real-world applications. There's lots of parabolas in the real world. It's often useful to find and interpret the inverse of a quadratic model. So one thing to note when working with real-world applications, it's often more useful to just switch the notation. So instead of x of y, the inverse would be y of x, instead of doing the negative to the 1 power. So in this case, we've got a function giving the distance that an object falls in t seconds. So then we're writing the inverse function. So first thing, we restrict the domain. Domain is the inputs. So in this case, our inputs are t. So that means we'd restrict t to be greater than or equal to 0. And then you find the inverse. So this is our inverse function. Notice how in the original function it's d of t. The inverse, we switch the letters, so it's t of d. Then it wants us to estimate how long it will take the penny to drop. So you'll plug in that distance into the function, and then you'll end up with the time. So here we have a function giving kinetic energy E in joules of an 8 kilogram object that is traveling at a velocity of v meters per second. We want to write and graph the inverse function to find the velocity required for the 8 kilogram object to have a kinetic energy of E, and then estimate that for 60 joules. So our original function, EV equals 4v squared, is a quadratic function. And then we have to restrict v to being greater than or equal to 0. So to find the inverse function, we replace E of v with E, divide both sides by 4. So we got E over 4 is equal to v squared. And then take the square root. So v will be the square root of E divided by 4. We just write v as v of E, and then we'll have E over 4. So that is our inverse function, square root of E over 4 for E greater than or equal to 0. In the next video then, we will finish solving this problem with the values that we're looking for.